Thanks a lot, Alessandro. Thanks to the organizers for putting on a great conference. I really enjoyed it. And thanks to the KITP for hosting it. So I wanted to talk about some work on a one-parameter generalization of the cusp anomalous dimension in planar n=4, in which we introduce an angle we call a tilt angle, and tell you its role in calculating scattering amplitudes for all values of the coupling. And they're equivalent to polygonal Wilson loops. And we're doing it in a particular region called the origin, which is not exactly like this picture, but I still kind of like the looks of it. This is work that started off in a paper with Benjamin Basso and Yorgos Papathanasiou around early 2020. And since then, been working with Yorgos and Yuting or Andy Liu and Gerald Dunn on some extensions of it, which I'll also describe here. And Yuting is here, is sitting over there, and he's a KITP graduate fellow, so he's at UCSB for 6 months. And so if there's any questions I can't answer before I skip town, you can ask Andy about it. Just a little bigger picture. I am interested in the scattering of massless quanta and gauge theories as plane waves scattering off each other because of its relevance for LHC physics. The LHC is the world's largest experiment. It's like 27 miles around the collider. But then at the sub-femtometer scale, this is what happens. 2 protons come in, and a lot of mess happens. But at the heart of the mess, there are probably 2 quanta, like partons we call them, quarks or gluons, that collide in some cases at very short distances and produce new particles. For example, maybe this is the Higgs boson here, decaying to a couple of quarks. And then as the quarks and gluons and other particles emerge from the collision, the quarks and gluons are confined. And eventually they don't appear as the outgoing particles. These green blobs represent hadrons, like pions and protons and so on. But there's this jet-type structure that emerges where the jets can be traced back to quarks and gluons at short distances. And so the goal of computational collider physicists is to calculate the short distance part accurately. The long distance part is non-perturbative, and we don't have very good ways of computing it. There are models you can make based on string models like the Loon model or cluster fragmentation. But, and then the short distance structure of the proton, that you can get from experiment, the parton distributions. But this inner part, you can calculate using Feynman diagrams in principle. But it's very complicated calculations because you may want to consider states with lots of outgoing quarks and gluons because multi-jet events are very copious at the LHC. So it's a big task to do these calculations in QCD, and planar n=4 super Yang-Mills has proved to be an excellent testing ground for some of the techniques that go into QCD calculations. And so that was a motivation for me for studying this theory, because it's a testing ground, but at the same time, it's a lot more fun because answers tend to be much more simple due to the underlying properties of conformal symmetry and quantum integrability, which have been seen in the context of anomalous dimension and the dilatation operator, as you know, since about 20 years ago. But now we want to sort of understand what are the structure of these scattering amplitudes in this theory. And as I'll mention, there are different sort of approaches to calculating these. And down here at weak coupling, if we're in the planar theory, it means we scale the Yang-Mills coupling to be small as we scale the number of colors to be large, holding lambda fixed. But then we can still vary lambda from weak coupling near 0 to very strong coupling. And in the weak coupling domain, we can use techniques that involve Feynman diagrams or other ways of rewriting the integrand that we would have gotten if we had used Feynman diagrams. And we know a lot about the analytic structure, order by order, and perturbation theory. So we can actually use some powerful bootstrap techniques to go up in order. But we also have limits where we can do things at finite coupling. And I'll say a little more later about the flux tube approach, which is a really kind of pioneering example of that, where you can build up the answer near a kind of collinear limit. And then we also heard from David yesterday about in certain collinear limits at strong coupling, you could try to carry out this expansion around the collinear limit and recover results for more general kinematics in the very strong coupling limit. And those involve minimizing the area of the worldsheet of the string description using ADS CFT, where the area goes like e to the minus the square root of the TÜV coupling times a classical action. And the problem of minimizing the area of this action is classical integrability. And we'll come back to that a little later. The general goal would be to calculate things in the middle somehow. That could involve resumming an expansion in this direction, could involve resumming an expansion in this direction, and we're not there yet. In this talk, I want to talk about another limit, which is also a kind of kinematic limit where things are solvable. In fact, they're in some sense much simpler than this flux tube approach, but more specialized kinematics. And we call these origins. So you can think of an origin as a line along here, just because it could also represent the flux tube kinematics. And there will be a proposal that's good for any coupling. And then we can, as I mentioned, we can do these perturbative calculations, in some cases up to 7 or 8 loops. And so then we have very stringent checks of an all orders proposal. So I'm going to just give the proposal at the beginning and then unpack it throughout the talk. The idea is that in suitable kinematics, after subtracting some overall divergent part of the amplitude in a particular way, the logarithm of the amplitude is quadratic in the logarithms of small kinematic variables. Now, the amplitudes for gluons, they depend on the helicity of the gluons. And this proposal is for the simplest non-vanishing helicity configuration, which we call maximal helicity violation. But it's not that important, although other cases will be definitely more complicated. So anyway, we propose that in suitable regions, the logarithm of the amplitude is simply quadratic in the kinematic variables that are getting large, that are controlling this region. So we're sending a bunch of variables we'll call ui to 0, and it's logarithmic in the ui's, but it's merely quadratic in logarithms. And furthermore, these quadratic terms are given by a master formula, which only involves one integration, and it's an integration which can basically be done by contour taking residues. So it's very simple. And then the integrand factorizes into 2 pieces, where this piece is going to end up being the tilted cusp anomalous dimension I mentioned earlier, and it depends on the coupling, and all the coupling dependence is buried in it. And then the kinematic dependence will be some rational function in Z, and it will have quadratic dependence on these logarithms. So yeah, that's what I just said. And in fact, this proposal is inspired by the strong coupling behavior. So it'll basically involve the classical string area density in these kinematic regions.
So this is all planar and G stuff.
Yeah, G squared is the integrability definition of the one that's used in it's lambda over 16 pi squared, and lambda is NCG Yang-Mills squared. Any other questions? So amplitudes in this theory, it's been known for a long time that they have a dual incarnation. They can also be calculated up to certain overall divergent factors, which you can remove in various ways. They can be calculated as the expectation values of a Wilson polygon, a polygonal contour expectation value around this some polygon, where the light-like edges here correspond to the massless or light-like momenta of the outgoing gluons here, which is pretty remarkable. And going along with this picture, there's a extra symmetry of these amplitudes because these points here have a conformal symmetry associated with them. So they transform like positions under a conformal symmetry action. In terms of momentum, we call this dual conformal symmetry. And it means that the scattering amplitudes depend on like 4 fewer variables than you might have thought, or 4 fewer variables than they would in the case of QCD. So this was first understood at strong coupling by Alday and Maldacena, and then it was verified to hold at weak coupling as well. Now, in fact, these scattering amplitudes and these Wilson polygon loops are both divergent, and the divergences are sort of dual to each other. The on-shell amplitudes are infrared divergent due to long-range gluons, and people encounter these kinds of infrared divergences all the time in collider calculations. But on the dual Wilson loop side, the divergence is an ultraviolet or a short distance divergence that comes from gluons propagating very close to a singularity in the contour at a cusp. So this is called the, well, these are light-like lines. So this is sometimes called the light-like cusp anomalous dimension. And that was computed using integrability by Beissert, Eden, and Staudacher. So we know its expansion to all orders, and we're going to have a one-parameter generalization of it that's going to play a role here. So both of these kinds of divergences can be removed by dividing by the same function. And we wrote down such a function. I'm not going to go into the details of it, but you can remove it and have the ratio maintain the symmetry I mentioned earlier, the dual conformal symmetry. It's actually anomalous for the full amplitude because of these divergences. But once you remove them in the right way, you get something that only depends on a much smaller set of variables. For example, in the 6-point amplitude, the full amplitude depends on if you regulate the divergences dimensionally, so d is 4 minus 2 epsilon, then you get many poles in epsilon. And the answer generically depends on Mandelstam variables, individual ones. But after dividing by this ansatz and taking epsilon to 0, you get a finite behavior for the remainder function, and it only depends on this smaller set of variables. So the dual conformal symmetry is generated by special conformal generators, but they're composed out of inversions of these dual coordinates. So if you want a function to be invariant, you mostly need to build it out of xij squareds. These are in the invariant distances between the corners of the polygon, and make sure that it's invariant under this symmetry. And that fixes the answer up to functions of invariant cross ratios, as is very familiar from ordinary position space conformal symmetry. The difference, though, is that we have this light-like constraint. And the momenta of the polygons are the separations of adjacent corners. And since those are light-like, we can't build any such variables for n equals 4, where you normally get 2 of them, u and v. And you can't even do it for n equals 5. But for hexagon, you have non-trivial dependence on these ratios. And sometimes we call them u, v, and w, or sometimes u1, u2, and u3. But here you can have a line between 2 next to adjacent corners, and then another one here, x1 3 squared, x4 6 squared, and then divide by x1 4 squared, x3 6 squared. These that correspond to 3-particle Mandelstams in the denominator and 2-particle Lorentz invariance in the numerator. And then V and W are just related by cyclic symmetry. And every time you add another particle or an edge, it has sort of three spatial momenta associated with it. And then the energy is determined by the on-shell condition. So when you go from n equals 6 to higher n, you get to add 3 variables for each additional leg of the heptagon, so of the polygon. So we get 3 ratios for n equals 6, 6 ratios for n equals 7, 9 for n equals 8, which are the cases we're going to consider here. So there's still a pretty rich kinematical structure even with 3 variables, but it's the only case I can plot kind of completely. So there are many limits that we've explored in this program. And this green one here is the near collinear limit. And we can construct perturbative amplitudes and constrain them on this boundary using the flux tube limit. And then we can move to this origin where U, V, and W are all going to 0. And that's the prototype for these kinematics that I'm going to discuss in the rest of the talk. Any questions? So this flux tube approach, which Davida mentioned yesterday, was pioneered at the OPE level by Alday Gallardo, Maldacena, Sever, and Vieira. And then Basso, Sever, and Vieira found finite coupling descriptions of the excitations that are based on the Gubser-Klebanov-Polyakov string. And as he mentioned yesterday, you can construct finite coupling results for these quantities by tiling an n-gon with a bunch of pentagon transitions. But in fact, we're gonna be quite a ways away from the flux tube region. You see the flux tube region, if you want to only have a small number of excitations contributing, it's in a region where 2 of the gluons are getting collinear, which turns out to be on this equilateral triangle here. Whereas we want to be in this self-crossing limit where things actually simplify even more, but they're not really describable in terms of single flux tube excitations. You have to do a kind of resummation. You want to get there. So the original example we found of this behavior was in the 6-point case where we sent these 3 cross ratios to 0 and found that this quadratic behavior perturbatively through 7 loops. It had previously been seen to be quadratic through 2 loops and also at strong coupling on the diagonal case where all 3 of these are equal. But here we could explore it for arbitrary ratios of the 3 variables as they go near the origin. And we found this quadratic behavior where the coefficients of these logarithms had anomalous dimensions, which we call gamma oct and gamma hex. You might wonder right now why we call this gamma oct if it's in a hexagonal Wilson loop. I'll get to that in a second. But then there's also a constant term C0. So each of these had a weak coupling expansion, which could be read off from knowing the sort of full amplitudes through 7 loops and moving towards the origin. And this octagon one had the curious property that it didn't have any odd zeta values in it. All of these things have what we call uniform transcendentality. That is, the index on the Riemann zeta value is 2 here, 4 here. Sorry, C is a constant, and it doesn't have 2 logarithms in it. Therefore, it sort of has 2 more indices, 2 higher indices. So if this is at 4, this one's at 6. And zeta 3 squared counts as the same sort of transcendentality as zeta 6, or transcendental weight. Anyway, there are these series of Riemann zeta values here for the weak coupling expansions. And most of the quantities have odd zeta values appearing in them, which kind of looks like the cusp. In fact, this one is the cusp here, this line. But then this octagon didn't have any odd zeta values in it. And we called it, yeah.
The Tufts coupling counting, how does it go in this table?
The Tufts coupling counting. Sorry, this is the loop order.
It's a loop order.
And so
okay.
this one goes like lambda G squared or lambda, and then G to the fourth or lambda squared, lambda
Yeah, okay.
and
That
so
makes
on.
sense.
Yeah, sorry for not making that clear. Yeah.
So this is kind of exact. What are the corrections to this formula? Because the first term dominates, right? So it's large.
Yeah. So this is
Then,
a leading log
Yeah.
behavior. There are no single log terms in the formula, and then there's a constant behavior, and then I should have put power law suppressed. So
okay.
order U.
But the second term is small if both U and
This one here,
yeah, the second.
this one
yeah.
drops out if you go on the diagonal,
Okay.
and then you just get this term. But when we go in this limit, we scale U1, U2, and U3 to 0 at the same rate, but we allow for arbitrary ratios. And then this term can be seen too. Any other questions? So this one that I showed here turns out to be the perturbative expansion of the logarithm of the hyperbolic cosine of 2 pi g. And it appeared earlier in the light-like limit of the correlator of 4 large charge operators. And this was first discussed by Frank Coronado, and then there's also been a lot of work by Kostov, Petkova, Serban, Belitsky, and Korchemsky, Barguer, Coronado, and Vieira, and probably quite a bit more since then. These large R charge correlators, the large charge sort of allows you to, first of all, think of the correlator as this being in this charge space, which is kind of on the S5 in ADS5 cross S5, and you have 4 of them. So you have a sort of picture of this like baby's jumper, and then but then you can cut it apart, and the wrapping corrections are suppressed in this limit. So it's really the square of something which is called the octagon, because when you cut it open, you get 8 sides there. And in the light-like limit, you get a log squared behavior with this exact coefficient. But why it's exactly the same as some piece of this origin limit of the hexagon is, I think, still kind of obscure. It showed up, actually, I forgot to put on, but it's been also seen and also gamma hex in some work by Pedro Vieira and collaborators on snowflake OPEs. But more recently, it appeared in yet another context, the form of a new version of the Pentagon OPE called the form factor OPE. And why it's showing up there too, I don't know. But it's like a baby version of the cusp anomalous dimension. It has the same qualitative behavior, weak coupling, strong coupling, but much simpler. But that's not the only one. We also have this hexagon term. Now to try to unify all of these different anomalous dimensions, we should go back to what Beisert, Eden, and Staudacher did in 2006. So they were describing this excitations on the spinning string, or GKP vacuum, or equivalently sets of twist 2 arbitrary spin operators in planar n equals 4. And this sort of picture led to exact anomalous dimensions for arbitrary twist 2 operators as well. But for the cusp, they found an integral equation for this spin chain, for the spin fluctuation density, which looks like this. And the solution then is computed by solving this equation and taking t to 0. But maybe another convenient way of expressing it is to expand the sort of t dependence in Bessel functions. And when you do that, this solution can be found by inverting a semi-infinite matrix 1 plus k, where k is just involves overlaps of Bessel functions with this e to the t minus 1 and t in the denominator. So that's the BES kernel. And the weak coupling expansion of this kernel can be carried out. And all these overlap integrals are weak coupling expanded in terms of these Riemann zeta values. And they somehow odd zeta values and even zeta values play a different role. So it kind of makes sense to think of splitting this semi-infinite matrix into a 2 by 2 block form, according to whether, sorry, I meant to say whether, yeah, I and j are odd or even. So this would be like odd, 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 even, odd, even. And these off-diagonal blocks will have I and j of opposite parity. So the sum will be odd, and this doesn't change it. So these will have odd zetas over here and even zetas over here. And of course, even zetas can all be reduced to powers of pi squared, but the odd zetas are somewhat different. So it makes sense to consider maybe modifying this kernel by weighting the odd terms differently than the even terms. And so the proposal for what these gamma oct and gamma hex and even gamma cusp should be thought of as is as specific examples of a one parameter deformation of the BES kernel, specifically this one here, where we weight cosine alphas and sine alphas and have an overall cosine alpha here. So if we do this, we find the weak coupling expansion can be carried out in the same way that you do for the regular kernel, and it agrees through 7 loops with the previous formulas, and also nice things happen out at strong coupling. So here's just an example of what the weak coupling formula looks like. It's got a bunch of, even Riemann zeta values, which could be written as pi squared, pi to the 4th, etc. But the formulas are nicer if you write them as Riemann zetas typically. And then the odd zetas start up at g to the 6th. And you can easily, get lots of data out here at weak coupling by taking bigger and bigger K matrices. And they all have similar kind of behavior at weak coupling. They have the same finite radius of convergence as the cusp anomalous dimension. And the cusp is the case of pi over 4. Because for pi over 4, everything in red here is 1 over the square root of 2. And you get 2 of them canceled by this one. But if you take alpha to 0, then you kill all the off-diagonal ones. And so then you only get powers of pi squared, and that becomes log cosh of 2 pi g. But there are other angles you can use too, and the one we need to get the hexagon turns out to be pi over 3.
Do you understand it sort of more fundamentally why it has to have this form?
Not yet, but we can still write down a formula that at least treats this angle as a kind of complete dynamical variable, and we'll see how it's localized on these values. Exactly why that's the right thing to do, not quite, but you'll see a little more as we go along. I should also say I'm not really going to talk much about the constants in the more general cases beyond 6-point, but in the 6-point case, we were able to find a representation of the expansion of the constants that makes a lot of sense, in the sense that instead of inverting the matrix, you take the log of the determinant of the matrix. And then you find the same angles appearing as appeared in the leading terms. The log squared terms depended on the angles value 0 and pi over 3. There's also the cusp term, and this guy is kind of depends on the normalization. In fact, before this whole origin story came along, we had some very independent reasons for trying to do a finite renormalization of the whole amplitude, multiplicative renormalization, or in terms of the logarithm, an additive shift. And we had already found a kind of perturbative expression that made a lot of the number theory work better. And we subtracted it off, and we found that it could all be reproduced if we just used sort of this normalization instead, up to some things that we weren't sensitive to in the earlier analysis. And so if you shift the overall normalization of the amplitude appropriately, you can wipe out the terms that involve the cusp angle of pi over 4. And then you're just left with the same sort of angles that appeared in gamma oct and gamma cusp. So now the question is, how do we go from that couple specific values of the angle to a more general formula that can generalize not just to 6 gluons, but to n gluons? And so this proposal has this contour integral of this quantity g, And it's basically just the same as this tilted anomalous dimension. You just, here we like to use a complex variable z, which is related to this tilt angle by minus e to the 2i alpha. So if we have a residue formula where we have a pole on the unit circle, then that will just correspond to a real value of alpha. And the formula is for this factor here is going to have a piece which is polynomial in z and 1 over z. So for example, it will have no poles on the unit circle. The only poles for this guy will be at 0 and infinity, and quadratic dependence on the LIs. And in the 6-point case, it has this very simple form. And then there's a kinematic independent prefactor that only depends on n. And this one provides important poles on the unit circle. There's also some poles here which involve the cusp anomalous dimension value. It turns out z equals I corresponds to alpha equals pi over 4. But those can be shifted around by different normalizations. And this one, I think, gets canceled by this. So these are really the important poles if you want to look at it on the unit circle. Now, so far, I didn't tell you what this contour was. And the contour we want to choose, which will be valid at any coupling, is this edge of this shaded region here, this C-shaped contour. So it avoids the real axis, and it goes around 0 and also goes around. And it has to be inside and outside of the unit circle. So now we have a couple choices for how we evaluate the contour when we go to weak coupling. We expect that this G function is going to have poles on the real axis for finite coupling. But when we go to weak coupling, we know that perturbatively, G, if we expand out K just had polynomial dependence on sine and cosine of alpha. And those are related through this exponential map to just being powers of Z and 1 over Z. So perturbatively, we don't have any poles on the axis. And then we can close these circles. And now we get a different contour, which just has 2 circles here. And now we have 2 choices. Also, I should say the integrand is manifestly symmetric under Z goes to 1 over Z. So the 2 choices we have is, one we can move these 2 contours near each other and then turn them into circles around the poles on the unit circle. When we do that, because the Z's are minus e to the 2i alpha, and Z is on the unit circle, alpha should be some real angle. And in the case of n equals 6, for example, we pick up poles here. These, and you also find some residues here that have the cusp anomalous dimension. That's kind of a normalization dependent quantity we understand pretty well. So the important poles would be like these 3 here. And if we go to higher values of n, you can see we're going to get poles which are, roughly speaking, 1 over 3n minus 4 roots of unity, or negatives of those. So we get more and more poles around the unit circle for higher and higher n. And when we do that, these residues naturally turn this G function into specific gamma of alphas. So we get a finite set of sums of gamma of alphas. But since the Z's are going to pretty weird angles, from the rest of the expression, you get very ugly trigonometric factors. But that's a sort of a good representation to continue it to arbitrary coupling. On the other hand, you can close the contour at Z equals 0, and the Z equals infinity residue is exactly the same. And when you do it around the origin, then you look at the perturbative expansion of this G of Z and alpha, and you manifestly only get like rational coefficients in front of the zeta k values. So there are some trigonometric miracles that go between here and here, but they're just a consequence of Cauchy's theorem, basically.
So to understand correctly, originally you have a bunch of poles on the real line.
At finite coupling, there are some poles here, we think. And
they move where?
They sort of just, I think they just move towards 0 and infinity as you take the coupling to 0.
And these are the only singularities that you have in the integrand?
That's what we think. I mean, we haven't really explored the finite coupling behavior exactly. We have that on our to-do list,
But at weak coupling, I mean,
at weak
you
coupling,
can
for
check
sure,
numerically
at
Cauchy's
weak coupling,
theorem.
there's nothing else there.
Yeah.
And we can also do strong coupling evaluations of these functions. And well, our proposal is actually built from strong coupling. So it has to reproduce the leading term in the strong coupling expansion.
So a strong coupling, the convergence properties are usually worse for the BS. Does it improve in this general case, or it remains tricky? Or
yeah, it's a great question. You know, it's at zero coupling has finite radius convergence, but around infinite coupling or small and 1 over root lambda, it's asymptotic series, and it's not Borel summable, which means that you can do a Borel transform, but it has a pole on like the real axis in a bad place. So you get ambiguities when you move around it. Those poles actually depend on the angle. So how fast it diverges asymptotically, that depends on the angle. And we've been studying that, but I actually didn't have time to write slides on it. So. But it's definitely something we're trying to follow up on and apply resurgence to possibly as well, which has been done for the cusp anomalous dimension by Acevedo and yeah.
Cool.
I'll show you, I won't show you all the polynomials in Z, but since you asked, so when we go to n equals 7, is that, yeah.
So far, I mean, so this 7 loops.
Yeah.
6 points.
Yeah.
But you say you have evidence that you will show us from strong coupling for this, because I mean,
yeah, that's right.
Okay. Then,
I'll get to that and also describe weak coupling checks a little bit more. But first, let me say, what is the analog of this origin when you go to higher points? Now, I really should have said that when you go to 7 points, there are these cross ratios, which are ratios of differences of x's. And there is naturally a set of 7 cross ratios that transform into each other under the natural cyclic symmetry of a heptagon. But there are only 6 dynamical variables. So there's a nonlinear gram determinant constraint on these variables. And in particular, you can't send all 7 of them to 0 without violating this constraint. So our motivation is send as many things to 0 as we can. And so we can send 6 to 0. And then the 7th one has to be equal to 1. But furthermore, and so if I sent U7 equal 1, that would be the U7 origin. But if I sent U1 to 1, that would be the U1 origin. But we find this origin-like behavior holds even on a line between these 2 origins. The gram determinant condition allows you to have U7 and U1 sum to 1. And you can have arbitrary values along this line, and you get the same quadratic behavior involving logarithms. Now, some of the logarithms in here, log U7 and log U1, are not actually singular along in the midpoint of this segment, but the formula still holds. And so in this case, instead of having sort of 2 kind of types of anomalous dimensions, we have 3. And this is not the sort of ugly trigonometric representation. So these things are linear combinations of the gamma, the relevant gamma alphas. And here's their expansion. And this we checked completely through 4 loops in the 7-point case. And then things start to explode when you get to 8 points. In the 8-point case, when you start writing down the natural cross ratio variables, you find that instead of there being sort of 1 dihedral orbit, there are 2. There are some cross ratios we call U1 to U8, which rotate into each other as you rotate the octagon. And then these guys rotate on a shorter cycle. And that means that you can find origins with similar numbers of 1s and 0s. In particular, most of them have 3 1s. And you can distribute the 1s and 0s in different ways, which are dihedrally inequivalent. So if I showed you this map for the 7 and 6-point case, there would just be one kind of origin and maybe a line origin as well in the 7-point case. But now we have all of these different origins. And furthermore, we find the same quadratic behavior on many lines, 2-dimensional surfaces and 3-dimensional volumes that interpolate between the corners. And, you know, finding all of these, you can use the Graham determinant constraints to say which ones are allowed, but to kind of move between them and understand the scaling, you can use some parameterizations that Bassos, Severin, Vieira developed, but there's also cluster algebra-based ones and mutation moves that move you from one place to the other to try to explore this space. This guy here we found by the Graham determinant, but we don't have, it seems to live outside a nice positive region, so we don't know exactly what to do with it.
Sorry, the first line is special somehow?
Yeah, I forgot to say, this one we sometimes call the super origin because it only has two. We think that this quadratic behavior, this is just empirical, seems to hold whenever you move from one point to another with the same number of ones. But this one is different. And the line between O1 and O2, it's not quadratic logarithm. It has more complicated behavior. But if you have origins that connect everything from O2 to O9, it always seems to be quadratic, at least the good directions we've found. We can't say we've done this systematically yet. And this is a little bit what it looks like. Thanks. So this O1 is in red. And so here we get non-quadratic behavior between O1 and O2. So there's kind of a line there, but doesn't have the same status as the rest of these lines. On all these other lines, everything's also quadratic. And then you can fill in various areas with two-dimensional surfaces and sometimes three-dimensional cubes. So for example, there's one we call the 6, 7, 8, 9 cube because it has 8 corners and you basically vary things from 0 to 1. And 2 of the corners are dihedrally equivalent to, or 06 type, 2 are 07, 3 are 08, and 1 is 09. And why there's this kinematic behavior and how much further it extends. We think some of this will extend to things further from these origins, but we don't know exactly how yet. And just to say that this master formula, we checked it to 7 loops. I mean, that was part of the construction. So, but we've since, with Andy, we've used a particular method to compute the 8-loop amplitude, and everything's consistent with the 8-loop formula. We also had a way of getting to 8 or 9 loops by resumming this case, the flux tube expansion. I'm not going to talk about that here. At n equals 7, I showed you one of the formula for the lines, and that one we could check to 4 loops. And the n equals 8 case, we can really only get to about 2 loops or so. And but we have many different limits. There's also some all-loop structural check, which I'll skip because of lack of time. There's a yeah.
This master formula, is there any conceptual understanding why it holds, or so far it's by inspections, or?
Well, that's what I'm about to try to describe.
I see.
Is that it basically comes from the classical integrability in the TBA, and you just have to do one leap of faith where you insert this tilted cusp anomalous dimension in the right way.
Yeah, so what makes me curious is that it's somewhat reminiscent of the factorization on the QCD, like as in soft collinear effective theory.
Yeah, that's true.
KRN, etc. But
by the way, you might say, is this region similar to the regions where people factorize soft collinear? But it's, you know, it's
different, or let's say,
yeah, I have to admit that this kinematic region, it's very Euclidean, not very Minkowskian, which makes it difficult to say it's exactly like some of these other regions. In fact, when we look in these other regions for the amplitudes, they're not as simple. The factorization happens, but it happens in a transform space. And when you expand it out perturbatively, you don't, and you take the log, you don't get quadratic behavior. You get better behavior, but not infinitely better. So it's controlled by different types of anomalous dimensions there. I mean, you have the cusp always appearing in Sudakov regions, which is what you're talking about. But then you have different kinds of anomalous dimensions for subleading logs and so on. So it's reminiscent of soft collinear factorization, but it seems to be a bit different.
I see. Thank you.
So we've seen these equations a couple times now. These are the general TBA equations for the classical minimal area problem. And the log of the amplitude is this minimal area multiplied by the square root of the 't Hooft coupling. And the kernels that enter have this sort of general structure. And if you were to do this in general kinematics, there are more definitions required. It's very complicated, requires some numerics. If you're in the right region, you can kind of iterate systematically and get very good convergence. Some other areas are difficult, but in the origin limit, the TBA simplifies drastically, especially when you do a Fourier transform to simplify the convolutions. So for n equals 6, you have a kernel which is just 1 over cosh of theta. And if you Fourier transform it, you get also cosh in the hyperbolic cosine in the transform variable. And the area formula turns out to be an integral of a source term with a function. It also depends on the source term with this kernel 1 over 1 minus k hat. And it just gives you, and this source term is actually linear in these logarithms. And so you just get a scalar multiplication. In the n greater than 6, you get a bit more complicated matrix of sources that involve multiple logarithms. But once you take this formula, which you can work out once you scale these different origins in the right way, sometimes it's a little tricky, but once you get the classical area formula in terms of as an integral over S from minus infinity to infinity, then we're going to change integration variables and use Z, which is e to the pi s over 2. So that runs from 0 to infinity. And now what we're going to do is we're going to insert a logarithm into the integrand. But because we're integrating on this contour, or we change the contour from being this line to this C, and then we get a discontinuity across here, which is just a constant for the logarithm from wrapping around there. So that allows us to put the logarithm in. And interestingly, I should have said we worked out the strong coupling behavior of this tilted anomalous dimension, and it has an alpha in the numerator, which is the logarithm of z, because z was minus e to the 2i alpha. So that gives us a logarithm, and then we get a z 1 minus z there. So basically, what we're going to do is take the area formula, recast in terms of z with a logarithm, and then we're just going to insert this tilted cusp anomalous dimension divided by the g goes to infinity limit. And this guarantees that we'll get the right behavior as g goes to infinity, because in that limit, we've only inserted 1. And that's where the proposal comes from. Now, why this is the right thing to do, that's the real question now. Okay, so then we basically just get this formula from that. So this all comes from looking at the classical TBA. And just to state, the weak coupling expansion can be obtained quite systematically by expanding out K, but it stops, the radius of convergence is only good out to 0.25, 1/4. But you can go to much higher values. The coupling is pointed out in this paper. If you truncate the matrix, but evaluate the matrix elements at finite coupling numerically, and then you can get much larger values of G. Now, out at strong coupling, as we were just discussing, the behavior is asymptotic and not Borel resummable, but we can find the location of the poles in the Borel plane from general considerations, or also from doing very high order expansions. So we can get about 150 terms at strong coupling now, but I didn't have time to describe that. So here's just some numerical plots for the cases that showed up in the in the 6-point case, but generally be similar for other angles. It's just that as you take alpha near pi over 2, this thing behaves worse, and the asymptotic behavior at strong coupling becomes worse and worse. This just shows a few terms and perturbatively, not as many. If we took as many as we have, it would go very close to the finite coupling values and then diverge very fast at 0.25. And then you can see, though, you can get good numerical agreement out at strong coupling with just, at this point, we only had 1 or 2 terms in the strong coupling expansion, but it's still asymptotic, and so you can't push down too far. This is also this determinant that shows up for constant terms. So just to wrap up, these origins are places where the scattering amplitudes simplify dramatically in planar n equals 4. There's a really rich kinematical structure starting at 8 gluons. There's this one tilted anomalous dimension and an associated determinant for constants. And we can do all these same coupling analyses. Of course, the big challenge is to prove or understand better why this simple insertion works in these kinematics, whether we can kind of expand around these kinematics and find different ways of simplifying things. I mean, these may be good limits for as sort of boundary conditions for perturbative computations as well. The NMHV amplitudes, which I didn't discuss at all, have a more complicated dependence, which we don't understand yet. And we're looking more at the strong coupling behavior of these coefficients and so on. So thanks a lot for your attention.
So let's have some questions.
So the standard cusp anomaly has various interpretations, like JKP string where you take log speed,
Yeah.
or two-point function. Well, it's the same thing. Is there anything similar to?
Yeah, I should have made a reference to. There's some work by Pedro Vieira on 6-point functions in CFT, where you go into a sort of triple OPE limit. They call it the snowflake limit. So you take two operators near each other 3 different times, and they see the hexagon showing up that way. So there may be some interpretation, and I believe they're kind of projecting onto very high spin operators. So it looks like it's related to a particular way of weighting an overlap or OPE coefficient of 3 high spin operators in some way. I mean, it's not a great answer, but it's the closest answer I know to how to maybe other ways to think about this.
So is there any physical interpretation of this origin limit and strong coupling? Like for the Reggie limit, for instance, you know, it's an infrared limit of the TBA. So
this is an ultraviolet limit, I think. I think it's much more.
I mean, you kind of you get rid of all these clouds of particles around it, right? So anyway, so there's an interpretation. I think it's infrared limit from the point of view of this system, 2D system. So for the origin limit, is there a similar interpretation?
I think it's a UV limit, and it has like these very large source terms or large chemical potentials, maybe. But that's what I think it is.
So this was the answer for the origin limit, no?
Yeah, for the origin.
Okay.
You're right. The Reggie limit is much more infrared.
Right.
There have been studies by some of these groups in Japan where they do this renormalization flow, which maps them. For example, in the 6-point case, they sort of start out at the on the diagonal, which is and usually a point where the 3 cross ratios are 1/4, 1/4, 1/4, and then it corresponds to doing kind of conformal perturbation theory around that point, and then they flow off near 100, which is the Reggie limit for the 6-point case. So these origins are much more sort of ultraviolet. I think.
Okay, thanks.
More questions? So since you have a bit of time, about the strong coupling and the resurgence, so you said that you have some work in progress. Can you briefly maybe tell something more?
Yeah, so Benjamin worked on the strong coupling limit of the cusp anomalous dimension back in the day, and he applied some very similar techniques here. And they basically involve introducing or doing some kind of a, not exactly Fourier type representation, but you need to calculate an auxiliary quantity which doesn't just depend on the coupling, but depends on T in some way. And as you go,
is T the Borel variable? Or, sorry.
No, T is, we're still working in the coupling plane. We haven't done any Borel transformation yet. So at each order in the expansion in 1/square root of lambda, I think T is the T in the the original formulation of the BES kernel. So then you do a kind of a double expansion in 1/square root of lambda and in T. And at each higher order, you need to keep track of a number of terms, which is equal to how many orders you are in the expansion. But he gave Andy and me a nice prescription for what to do, and we were able to push it out to pretty high order.
I see.
So we can get all these coefficients analytically to about 30 terms in the strong coupling expansion, and then they just become too big to store. And then we go numerical for specific values of the angle, and we can go to much higher orders. And the general rule is that the asymptotic behavior gets worse and worse as this angle starts to approach pi over 2.
I see.
And you can kind of see that on those numerical plots here. At least that's for gamma. We haven't looked at D as much. We did some of the very low order expansion of D in the previous paper. But here you see this behavior. And let's see, what else can I say?
So there was a story by Aristotino Vendorigoni with the resurgence, that's something similar.
That's something we still need to do.
I see.
So yeah, but Gerald has taken our formulas, I mean the numerical results, and he's done the Borel transformation. And then there's a particular conformal map that you can do that moves all the Borel plane singularities off of the real line, puts them on a unit circle.
Mm-hmm.
And then you can look for things to converge to various parts of the circle. And doing that, you can find evidence not only for sort of there's like a leading singularity, which you can, even people who don't know about Borel analysis I can find that one pretty easily. And then but you can see these subleading singularities there, and they have a systematic dependence on the angle for the various angles we looked at. But we haven't gone through really a resurgence analysis yet.
Yeah.
In the standard cusp anomaly, there are exponential corrections which go something like exponent minus 1/4 square root of lambda. This non-perturbative term is a strong coupling spectrum.
Oh yeah, I could tell you a little bit about what the strong coupling coefficients look like, because you know there's this K constant that shows up in the cusp.
Yeah.
So those get replaced by like kind of harmonic sums, like psi functions, evaluated at points that are shifted by this angle.
But I was asking about exponential corrections. Strong coupling.
Sorry. Yeah.
Because for the cusp.
So this Borel plane singularity analysis tells you what accompanies the exponential, and it's like 1 minus 2 alpha over pi.
Oh, okay.
So when alpha is small, I mean it's like I think it's like a square root for the cusp, but that, because it becomes like a half. 1 minus 2 alpha over pi, alpha is pi over 4, comes 1 minus a half or a half.
So you're talking about singular position of singularity, right?
I'm talking about what's in front of the e to the minus something square root of lambda.
Okay.
Isn't this what you're asking about?
Yeah, that's what
So
I was
it looks like this. Okay, 1 minus 2 alpha over pi. So pi over 2 is a singular region because these things are not really suppressed much at all as you go into that limit.
But for the standard cusp, there was some interpretation of exponents dynamic margin, plus scale from the OF.
So you're asking about the interpretation of these different exponents. Yeah, I don't know. I don't know if we have a good interpretation of what these mean. That's a good question.
Okay, in view of time, I would suggest to thank Lance again.